Welcome back, students. Today in this session we are going to solve some of the exercise questions from chapter number 7. So starting from exercise 7.1. 7.1, question number 3. AD and BC are equal perpendiculars to a line segment AB so that CD bisects AB. Exercise 7.1, question number 3, solution. First, we will write down the given information, that is given AD and BC are perpendiculars to line AB. So AD is perpendicular to AB. Also, BC is also perpendicular to AB. That is, AD is perpendicular to AB and BC is perpendicular to AB. So obviously this angle A and angle B will be 90 degree. And also from the figure it is given that BC equal to AD. To prove, we are going to prove that CD bisects AB, that is AO equal to BO. Proof. To prove, let us consider the two triangles, that is triangle AOD and triangle BOC. From these two triangles we get measurement angle AOD equal to measurement angle BOC, because they are the vertically opposite angles. They are vertically opposite angles. Also measurement angle DAO equal to measurement angle CBO. It's being 90 degree. And then AD equal to BC. This is the given information which we have earlier noted here. So by AAS congruence rule, there is angle side congruence rule. Two angles and one side is equal. So by AAS congruence rule, these two triangles are congruent to each other. That is, triangle AOD is congruent to triangle BOC. Therefore, AO equal to BO. If these two triangles are congruent, then BO is equal to AO. That is, hence line CD bisects AB such that BO equal to AO. Hence CD bisects AB. Next, exercise 7.1, question number 8. In right triangle ABC, right angle, let's see, M is the midpoint of hypotenuse AB. C is joined to M and produced to a point D such that DM equal to CM. Point D is joined to point B so that triangle AMC is perpendicular, is congruent to triangle BMD. Roman number 2, triangle DBC is a right angle. Roman number 3, triangle DBC is congruent to triangle ACB. And Roman number 4, CM equal to half of AB. So question number 8, solution. Roman number 1, here we are to prove that triangle AMC is congruent to triangle BMD. So in triangle AMC and in triangle BMD, we have DM equal to MC. This is the given information, DM equal to MC, and also BM equal to AM. Let me first write AM equal to BM, since M is the midpoint of AB. M is the midpoint of AB. This one also, let me write MC first and MD. Then measurement angle DMB and equal to measurement angle AMC. These are the vertically opposite angle. Vertically opposite angles. Now in these two triangles, triangle AMC and BMD, side MC is equal to MD and AM is equal to BM, and side AM is equal to BM, and also the angle DMB is equal to AMC. That is two sides and the included angle of these two triangles are equal. So by SAS congruence rule, these two triangles are congruent to each other. So triangle AMC is congruent to triangle BMD. Now next, Roman number 2. In Roman number 2, we are to prove that angle DBC is a right angle. So looking at this two triangles again, there is triangle AMC and BMD, measurement angle DBM, this one, and the measurement angle CAM are equal. Since these two triangles are congruent, these two angles are equal. Therefore, this line segment, that is side TB and side AC, are parallel to each other, since these two angles are alternate angles. So in Roman number 2, here side DB is parallel to side AC, since measurement angle DBM is equal to measurement angle CAM, and these two angles are the alternate angles. So this line segment DB and AC are parallel to each other. These two angles are equal, and being alternate angles, these two line segments are equal to parallel to each other. alternate angles. Now these two lines are parallel to each other. We have measurement angle DBC plus measurement angle ACB equal to 180 degree. This measurement angle DBC and ACB is 180 degree. Being these two lines parallel to each other, these two angles are the co-interior angles. That is, the sum of these two angles will be 180 degree. Implies measurement angle DBC plus measurement angle ACB. ACB is 90 degree. This is given in the questions. So measurement angle DBC equal to 180 degree minus 90 degree. That is 90 degree. So measurement angle DBC is 90 degree. Next, Roman number 3, triangle DBC is congruent to triangle ACB. We have to prove that these two triangles are congruent to each other. So in triangle DBC and triangle ACB, triangle DBC and triangle ACB, these two triangles are congruent. We have to prove that. So in these two triangles, side DB is equal to side AC. How can we say that these two sides are equal? Because in Roman number 1 we have proved that triangle DBM and triangle ACM are congruent to each other. So according to that, side DB is equal to side AC, being the corresponding parts of the congruent triangle. So next, side BC is equal to BC, that is, they are common side, common to both the triangles. Next, angle DBC is equal to angle ACB. Angle DBC is equal to ACB, that is 90 degree. In Roman number 2 we have proved that angle DBC is also 90 degree. Therefore, by SAS congruence rule, these two triangles, that is triangle DBC and triangle ACB, are congruent to each other. Now Roman number 4. In Roman number 4 we are to prove CM is equal to half of AB. CM is half of AB. For that, AB equal to CD. AB equal to CD. Why AB is equal to CD? Because these two triangles DBC and ACB are congruent to each other. So being the corresponding part of the two congruent triangles, they are equal to each other. This implies we multiply both sides by half, so it becomes half AB and half CD. Implies half AB equal to half of CD is CM, because M is the midpoint. Half AB equal to CM. Hence shown. Next, exercise 7.2, question number 4. ABC is a triangle in which altitudes BE and CF, two sides AC and AB, are equal, so that Roman number 1, triangle ABE is congruent to triangle ACF. Roman 2, AB equal to AC, that is ABC is an isosceles triangle. So looking at the figure, it is given that the altitude BE and CF are equal to each other. And then according to this information, we are to prove triangle ABE is congruent to triangle ACF. Let us see how we are going to prove this. So exercise 7.2, question number 4, solutions. So first part, that is Roman number 1. Here we are going to prove triangle ABE. Triangle ABE is congruent to triangle ACF. So in these two triangles, triangle ABE and ACF, side BE equal to CF. Side BE equal to CF. This is given in the question. And measurement angle BAE. BAE is equal to measurement angle CAF. CAF. This is because they are common to both the triangles. And also measurement angle BEA. BEA is equal to measurement angle CFA. CFA. It's being 90 degree. Since they are the BE and CF are the altitude to the side AC and AB respectively. Now therefore by AAS congruence rule, these two triangles, that is triangle ABE is congruent to triangle ACF. For the second part, it is Roman number 2. We are to prove sides AB is equal to AC, such that triangle ABC is an isosceles triangle. So it is obvious that since these two triangles, that is triangle ABE and ACF, are congruent to each other, AB is equal to AC. AB is equal to AC, since they are the congruent parts of the congruent triangles ABE and triangle ACF. So AB equal to AC, since triangle ABE is congruent to triangle ACF, and AB and AC are the corresponding parts. Since AB and AC are equal triangle, therefore triangle ABC is an isosceles triangle. Is an isosceles triangle. Next, exercise 7.2, question number 1. In an isosceles triangle ABC with AB equal to AC, the bisectors of angle B and angle C intersect each other at O. Join A to O, so that Roman number 1, OB equal to OC, and Roman number 2, AO bisects angle A. Number 1, solution. In the question, it is given that ABC is an isosceles triangle. So, triangle ABC is an isosceles triangle in which AB is equal to AC. And also the bisectors of angle B and angle C intersect each other at O. Bisector of angle B and angle C intersects each other at O. Now join A to O. That is A to O. Then we are to prove that OB equal to OC and OA bisects angle A. Since OB and OC are the bisectors of angle B and C respectively, these two angles will be equal to each other and these two angles will be equal to each other. Now let us try to prove the first part, that is Roman number 1. OB equal to OC. You know that AB equal to AC. Since ABC is an isosceles triangle and it is given that AB is equal to OC. Since AB is equal to OC, measurement angle ABC is equal to measurement angle ACB. Why? Because angles opposite to the equal sides are equal. Implies we multiply both this side by half angle ABC. Half of angle ABC is equal to half of angle ACB. Implies half of angle ABC is either angle ABO or OBC, and half of angle ACB is either angle ACO or BCO, because these two angles are equal, since OB and OC are the angle bisector of these two angles, that is angle B and angle C respectively. Therefore, half of angle ABC is equal to angle CBO equal to half of angle ACB, that is BCO, angle BCO. Implies now angles OBC is equal to OCB, that is, from this we can conclude that side OB is equal to side OC. Why? Because sides opposite to the equal angles are equal in length. This is one of the property we have learned in the earlier session. So side OB is equal to side OC. Now for the second part, there is we are to prove that this line segment OA bisects the angle A. That same as this one. Again, measurement angle ABO will be equal to measurement angle ACO. This can be deduced same as this one. So measurement angle ABO is equal to measurement angle ACO. Now in triangle ABO and triangle ACO AB equal to AC. It is given in the question, given information, and OB equal to OC. There is OB equal to OC. We have just now proved that OB equal to OC, and measurement angle ABO. Measurement angle ABO equal to measurement angle ABO equal to measurement angle ACO. Just now we have also proved that this ABO, angle ABO is angle ACO. Now by SAS congruence rule, triangle ABO is congruent to triangle ACO by SAS congruence rule. By SAS congruence rule. Now since these two triangles are congruent, angle BAO is equal to angle BAO is equal to angle CAO, being the corresponding angle of these two triangles ABO and ACO. That is, these two angles are equal in measure. Implies, since these two angles are equal, this OA, there is OA, or OA bisects the angle A. Hence, so next, exercise 7.3, question number 3. Two sides AB and AC and median AM of one triangle ABC are respectively equal to sides PQ and QR and the median PN of triangle PQR. So that Roman number 1, triangle ABM is congruent to triangle PQN, and Roman number 2, triangle ABC is congruent to triangle PQR. So question number 3, exercise 7.3, question number 3, solution. In the question, it is given that side AB is equal to side PQ and side BC is equal to side QR, and the median AM is equal to the median PN of triangle PQR. First, in Roman number 1, we are to prove triangle ABM is congruent to triangle PQN. So Roman number 1, solution. It is given that BC equal to QR. That is, BC equal to QR. This is given in the question. Implies half of BC is equal to half of QR. Implies half of BC is BM and half of QR is QN, since M and N are the median of BC and QR respectively. So BM is equal to QN. So in triangle ABM and triangle PQN AB equal to PQ. This is given, and AM equal to PN. This is also given, and BM equal to QN. This is, we have just now shown that BM equal to QN. So by SAS congruence rule, SSS congruence rule. These two triangles, triangle ABM is congruent to triangle PQN. That is by SSS congruence rule. Now for the second part, it is we have to prove triangle ABC is congruent to triangle PQR. For Roman number 2, in triangle ABC and triangle PQR, AB equal to PQ. This is also the given information. And BC equal to QR. BC equal to QR. This is also given information. And then angle ABC equal to angle PQR, because since triangle ABM is congruent to triangle PQN, we have proved that triangle ABM is congruent to triangle PQN. Therefore, this angle B will be equal to angle Q, that is, they are the corresponding parts of the congruent triangle. Now, by SAS congruence rule, triangle ABC is congruent to triangle PQR. That is by SAS congruence rule. Next, exercise 7.4, question number 5. In figure 7.51, PR is greater than PQ. That is, side PR is greater than PQ, and PS bisects angle QPR. Prove that angle PSR is greater than angle PSQ. So exercise 7.4, question number 5, solution. In the question, it is given that in triangle PQR, PQ is less than PR. That is, PR is greater than PQ. And also, PS bisects angle P. That is, angle QPS is equal to angle RPS. So these are the given information according to the questions. Now we have to prove angle PSR is greater than angle PSQ. So solution, here angle QPS is equal to angle RPS, since PS bisects angle A, and PR is greater than PQ. This is the given information. Implies angle PQS is greater than angle PRS, because angle PQS is opposite to the side PR, and angle PRS is opposite to the side PQ. And since PR is greater than PQ, the angle opposite to the longest side will be greater than the shortest side. So angle PQS is greater than angle PRS. Implies angle PQS plus angle QPS is greater than angle PRS plus angle RPS. We are adding angle QPS on the left hand side and angle RPS on the right hand side of this equality sign. This does not affect the equality sign. Why? Because angle QPS is equal to angle RPS. Now implies, let's see these two angles, that is angle PQS and angle QPS. PQS and QPS. These are the two angles we are adding. So this two angle will be equal to the angle PSR. This addition of these two angle will be equal to angle PSR. Angle PSR. Why? Because the sum of two interior angle opposite to this exterior angles. So likewise, this angle PRS and angle RPS will be equal to the sum of angle PSQ. Angle PSQ, same as before, because the exterior angles is equal to the sum of the interior opposite angles. Implies PSR is greater than angle PSQ. So hence, in this question you have to understand that an exterior angle is equal to the sum of the two opposite interior angles. So the addition of angle PQS and angle QPS is equal to angle PSR. Similarly, the addition of angle PRS and RPS, that is the two interior angles, is equal to the sum of the opposite exterior angles, that is angle PSQ. Hence, so next exercise 7.4, question number 6. So that of all line segments drawn from a given point, not on it, the perpendicular line segment is the shortest. So exercise 7.4, question number 6, solution. Let us take a line L and a point O which is not on the line L, and we draw OP perpendicular to the line and some other few lines which is not perpendicular to the line L. Let us suppose this is OQ, this is OR, and this is OS. So we are to prove that OP is the shortest among this other line, that is OQ, OR, and OS. We are to prove OP is the shortest line, then OQ, also OP is the shortest line compared to OR. OP is the shortest compared to OS. Let a line, let L be a line in which O is a point not on the line, and OP is perpendicular to line L. Then we are to prove OP is less than OQ and OP is less than OR and OP is less than OS. So in triangle OPQ, measurement of angle P is 90 degree. There is the others two angle, there is the remaining angle PQO and POQ in triangle OPQ will be less than 90 degree, and these two angles will be an acute angle. Therefore, angle Q is an acute angle. Why? Because the remaining two angles sum up as 90 degree. So these two angles will be less than 90 degree. So angle Q is an acute angle. Therefore, angle Q is less than angle P. Angle Q is less than angle P. There is side OP is less than side OQ. Why? Because side opposite to the greater angle is longer. Since this angle is greater than, that is angle P is greater than angle Q, so the side opposite to angle P, that is OQ will be greater than the side OP. Therefore, OP is less than the side OQ. Hence, we prove that the perpendicular line is the shortest among the other line. Similarly, we can prove the other two lines, the OR and OS is also greater than the line OP. Hence, similarly, OP is less than OR and OP is less than OS. Hence,